So this is version 1 of the term test, and I'm going to go through some student solutions for some of the problems that students had more issues with. So as I mentioned in the version 1 video, this is a piece of art that you can find if you just Googled this name in the Bridges Conference. I colored it a little bit differently just for the purposes of making enough contrast and getting it to print properly with our printing restrictions. However, it looks more beautiful in its original coloration. And the other class got the same diagram just with different kind of coloration. So we are told in part A that this corresponds to G, and of course G has order 8, and we're asked to sketch a Cayley graph. So it seems like most students just kind of recognized this as D8 or D4, basically the dihedral group of order 8. The main way you can recognize that is by dividing it into 4 and then noticing the way the diagonals go in each piece. Now, we are told here to choose one representation, either the Cayley graph or the multiplication table, to demonstrate how the product construction works. So I think I grabbed one of the pictures, or a picture of a student solution to this one. Let me see if I can grab it. No, not there. Maybe I did not. No, I didn't grab this one. Okay, this one was quite well done. Generally, we did a lot of examples of this in class, so this was pretty well done. I should have kept the last screen grab because that was the one that I wanted. Okay, is there a homomorphism from D3 cross C3 to K4 onto K4? Okay, so in this case, I'm not actually using the G that I constructed above, but it is kind of close to G. Right? So this student had a really nice answer. They used, when we want to find that something doesn't exist, one of the tricks that we can use is to compare orders. Like I talked about in the version 2 solutions, another way is to look at the properties of homomorphisms or properties of the groups that the homomorphism is supposed to be between and compare them. In this case, I can look at, well, one of the properties is order, how big those groups are, and see if those maps can actually exist. So I check the order of each of the things. The order of D3 cross C3 is equal to 18, and the order of K4 is equal to 4. So that means that if there is a homomorphism, then there has to be a kernel that gives us the first isomorphism theorem, or I guess the fundamental homomorphism theorem. Okay, and so then the orders under that isomorphism have to match. Under an isomorphism, everything has to be the same, the left or the right. So we have D3 cross C3 mod the kernel is isomorphic to K4, so their orders are the same. So ultimately, we get that the order of the kernel has to be equal to 18 over 4. But the order of the kernel has to be an integer. So, and then as the student really nicely says here, we cannot split 18 elements into 4 sets with the same number of elements. So that means that we just simply cannot construct this homomorphism. So here we see that like even putting a relatively weak condition like a homomorphism has to be onto can be problematic. It often doesn't exist because anytime we are in a situation where the order of the first does not have appropriate divisional properties with the order of the second, things aren't just going to work out, or things just aren't going to work out. Okay. The second one also has to do with the cycle graph, and I think that I basically went through it already. Now, this making connections question is one of my favorite questions, but I think that the vast majority of section 1 disagrees with me. But I would encourage you to look at this with like new eyes. My goal was not to trick you. It was to give you an interesting situation where you could see a group that you're quite familiar with summarized, right? This is the D4 group, one that you've been working with a lot, one that you're very, very familiar with. But the goal here is to just puzzle out, okay, what's represented where? How are they getting? Okay, so in this problem, we are told several things about these rosettes. We are told that the corners represent the whole group. The other borders, left and right borders, these ones, or maybe I just want to align it. Okay, so these ones are all the elements of D4. So there's 8 of them total. These are the left cosets, and these are I guess are we told what that is? Okay, so remainder of the top and bottom rows, okay, non-trivial subgroups of D4. Okay, yeah, so these are all the non-trivial subgroups of D4. Sorry, not cosets. These are non-trivial subgroups. So maybe I should actually circle that so we know. So subgroups. Maybe I might as well circle the elements too while I'm at it. Elements. And then that leaves the interior for cosets. And it might seem kind of strange because cosets are actually all shaded in a single rosette. And the reason we can shade them all in a single rosette, remember, is that cosets partition a group, right? So if the elements are just one shaded petal of a group, then a coset, a single coset, can partition the entire group. It can just represent one of these rosettes. Okay, so this was the first one, and I think a lot of people just struggled to see how the action worked out here. And that maybe led them to just a place where they were confused about the whole thing, and that can really throw you off. But there was like a big hint here. The elements in this representation of D4 can represent both positions and actions. Okay, and there are different ways of understanding this group, don't get me wrong, but I think that the easiest way to understand it is like this, in positions and in actions. So for example, one of these is going to tell us the action, and I actually don't think it matters which one. I think you can probably interpret it either way, but I think action first and position second. Okay, so what action could this lower leaf thing possibly represent? Well, remember that our identity is way up here. Okay, so the question becomes, how do we get from the identity to our red leaf? Well, there are different ways that we could do it. One way that I see it right away is to, if this is our line here, we can just flip along that line, right? And if we flip along that line and then rotate, then we will get back here, okay? So for me, that's a flip. I don't know. Flip along that line and then rotate. Maybe I think about rotating like a full leaf pair. So 1, 2, rotate 2 times, okay? So if I then take this and flip it along the same line and then rotate it twice, I should have said counterclockwise, I guess, I end up at the desired spot. Okay, and then again, if I take the second one as an interpretation of the action, okay, so what's the action required to get to the red colored rows from the identity? Well, the action required to get there, again, I could think of it a number of different ways. I usually think about flipping along the closest line. So I flip here, and then maybe I just like rotate half a petal. Is that an okay way to do it? I think so. Okay, rotate half a petal clockwise. Okay, so if I then flip along this line, I end up over here. Oops. And then rotate half a petal counterclockwise, I end up right here where the red petal is. Okay, so the idea here is that you do action, then starting position. Okay, so let's bring up a student solution for the next part, that H1 is a normal subgroup. Okay. So to show that H1 is normal in G, we want to check that all left cosets of H1 are the same as right cosets of H1. Okay. So from the figure, we can okay, so it says we can get right coset from row 4, column 2. And I should also mention that this student had kind of a directory to show us their symbols that they used. Okay, I didn't copy that though. Okay, so okay, let me just get my grounding here. This figure is all left cosets is equal to all right cosets. Okay, so we want to show that this subgroup is normal, so we want to check that all of the left and the right cosets of this guy are equal to each other. Okay, so we could start from several different places. One way is to just kind of look around, right, and see that, like, look, this coset is here, this coset is here, it's here, right? It's kind of always preserved in this bottom row, right? And the bottom row represents exactly the cases where we have normal subgroups, where we have the left equaling the right. Okay, so everywhere where we have cosets with the left equaling the right, H1 is involved. And further, we have exactly 4 of them, right? So that's enough to fill up our tank. And I think that what this student is saying is that we end up getting all of the required elements, I guess, or we get all the required generators in this way. It's kind of a confusing question. In some ways, to repeat, I think a lot of these visual things are, right? Because you can see them, but how you describe it to someone is a different question. Okay, how does this artwork demonstrate that there are exactly 4 non-trivial subgroups, D4 mod H? In order to make D4 mod H non-trivial, H must be a non-trivial normal subgroup. In the final row, interior, we get H1, H2, H3, H4. B4 normal subgroups from non-trivial quotient groups. Okay. So I guess that they are saying that these normal subgroups correspond to exactly one of the normal subgroups. So the subgroups in the bottom row are exactly normal. And that makes sense because we see that the red in the bottom row versus the second bottom row has the same shape. Now, I want you to notice something about the symmetry in the subgroups versus the normal subgroups versus the non-normal subgroups. So when we have the non-normal subgroups, we have these guys do have some kind of symmetry to them, but they're very, very close, right? Especially these ones, they're very close. So their subgroups don't really have enough control to be normal. This one kind of lacks that symmetry, right? It kind of lacks the symmetry that we've come to love and expect out of groups, as does this one, right? They're a little awkward. So visually, that is why we end up getting non-normal subgroups here. Throughout the bottom row, all of these subgroups are quite symmetrical, right? They're kind of quite almost exactly the number that we would like. Okay. So we have another homomorphism question here. Write an homomorphism and explain why it has to be an isomorphism. I'm going to put this here, and then we might have maybe a lucky one. Okay, so here's solution. So in this question, we have D4 mod H3, so there was a correction that was made to D4 mod H2. And we're wondering if there is a homomorphism, how can you then guarantee that it's going to be an isomorphism? Do you have enough kind of knowledge to be able to show this? So in rosette, I was trying to figure out what this word meant, but it said in rosettes, we have a phi that brings this rosette to that rosette. Yeah, and then if we have a map from here to here, it has to send the identity to the identity. So what's the identity in D4 mod H2? It is really just the group H2 plus H2 or times H2. More accurately, it's G times H2, where G is an element of H2. Okay, and so if H2 contains elements. Let me watch over them again. So if H2 contains elements that look like this, then maybe we can exchange some elements, okay? And then from there on, it's kind of obvious what we're going to do because everything kind of has the same number of elements, and it's more or less predictable. Okay. The students said a lot of interesting things, mostly correct, but yeah. Okay, so the idea here is to just like look at the picture. Obviously, these two are the same things. They only differ by, I guess we're looking at H2 and H3, aren't we? They only differ by a little rotation, actually, right? So even though they're only different by this tiny amount, we end up having more control than we thought. Okay. Yeah, okay, so I think I'll leave it there with this test. I know that this question was a challenge, but take a look back at it, and I think you'll find some really cool things about the pattern and the thinking behind making a travel D4 with you. Okay, take care.